Electrical transmission. This is about 3 words: transformers, high voltage, and alternating current. Faraday's law dictates how we can generate voltage in a coil by changing a magnetic field through that coil. In a generator, we can change the magnetic field in that coil by rotating it. This is what we learned about in the last lecture, how we make a generator. A coil rotates in a magnetic field, and that changing voltage drives a current through a light bulb, for instance. And if we have a regular commutator, we have AC current. And so remember, AC current is in line voltage is 120 volts, and it oscillates 60 times a second. So why do we want alternating current? It's a 3-step reasoning process that we'll explore in the next slides. We'll find that high voltage reduces power loss in transmission, and transformers are necessary to change voltage to make high voltage, and transformers only work with AC. That's why we need AC. Electricity is the highest quality energy by conversion efficiency. For instance, electric heaters can transform electricity to thermal energy with 100% efficiency because you can put the electric heater right in water, for instance. Electric motors can convert electricity to kinetic energy with 95% efficiency, sometimes better. So this is a great energy, but the disadvantage is it's not easily stored. It's not cheaply stored, so we have to use it when we generate it. You know, we may want our electricity over here in Bakersfield, but we're going to generate it here by the coast, or we'll have a nuclear facility here, and so we need transmission lines to go long distances to bring our electricity to consumers. It's good to know the USA grid is about 93% efficient, or 7% of the energy is lost, and we want to minimize this loss. The electricity that comes out of a generator facility is about 10,000 volts. In order to transmit it long distances, we then step the voltage up to about 500,000 volts, and we step it back down to bring it to your house, eventually down to the 120 volts AC that you get. Higher voltage means less power loss, and that's why we boost up the voltage. Let's take a look at why that's the case. What we remember is power is current times voltage, or because we can make this substitution, it's also equal to current squared times resistance. So what that means, if we're driving current through a pipe, if we're driving electrical current through a cable, the amount of power lost in pushing the current through the cable goes like the current squared. So if we were to transmit power from a power plant a long distance to a house, we recognize that the power transmitted is the current times the voltage. So if we want to lower the current, we can just raise the voltage up and transmit the same amount of power. So if we make the voltage very high, let's say we multiply the voltage by a factor of 10, we could transmit the same amount of power with 1/10 the current. And if we can cut that current down by a factor of 10, we cut the power loss in the lines by a factor of 100. So it's very important that we boost up our voltage as high as possible. This is another problem for you to work on that's essentially the same one. So what we want to do is boost our voltage up as high as we can so we can drop the current and drop our power losses. And we're going to increase that voltage until we get corona discharge. Now what's corona discharge? It's not electrical breakdown, which is arcing. Okay? Corona discharge is when the voltage gets high enough, you begin to leak electrons off the wires. And this is a power loss. And so what's going to happen is, in designing your long distance electrical transmission lines, you're going to boost the voltage up until you get to a point where your corona discharge is losing money for you. And so the voltage we usually use for long distance lines is about 500,000 volts or 500,000 volts. This creates the need for transformers because we can't generate electricity at 500,000 volts, and we can't use electricity in our houses at 500,000 volts. So we have to be able to step the voltage up to transmit it and then step it back down. This requires the use of a transformer. So how do transformers work? Let's say you want to increase your voltage. So this is where you have your primary source, and then you wrap a couple wires around a core, an iron core, and you have more wires on this side. This is a step-up transformer, and you'll get more voltage out than you put in. In fact, the voltage out that you get is equal to the input voltage times the ratio of these number of turns. And so if this is 3 and this is 6, this would be a step-up transformer. 6 over 3 would be 2, and you would double your voltage through this transformer. So this is great, but how does a transformer work then? These wires don't touch each other. There's only this iron core that goes through the loops of both sets of wires. And so what we remember is that we can induce voltage in a coil by changing a magnetic field. And so what happens is this electromagnet generates a magnetic field. It goes through this coil and generates an output voltage. But it's the change of a magnetic field that creates this voltage. So if we hook up a DC power supply here, we'll get, well, one, we will melt the wires with all the current that will flow, but we'll get no voltage on the secondary coil, only a big spike when we first hook it up, because that will make a changing magnetic field. And so we understand then, in order to make a transformer work, to change the voltage from V1 to V2, we need AC. And so that's the reason we need alternating current, because it's the alternating current that will make a changing magnetic field, and that changing magnetic field will create a secondary voltage in the secondary coil, allowing us to step voltage up, such as this one, for long distances, and then step the voltage down for our use. So for instance, if you've ever seen a garbage can size container at the top of a telephone pole, it's a good bet that's full of transformer that is changing the voltage to step it down so it can come into your house at lower voltage. So how does this work with the conservation of energy? When I step up voltage, do I step up power? Am I creating power? Am I increasing power? Of course we can't do that. So if the voltage steps up, the current must step down. So when you draw 1 amp here, you'll have to produce 2 amps over here in order to supply you with your 1 amp. So if the voltage is stepped up, N2 over N1, the current is going to be stepped down, N1 over N2. So why do we have alternating current? This is the reason. In the 20th century, we wanted to transmit electricity long distances, and we needed high voltages for that, and that's why we needed AC for transformer technology. However, now we have power electronics, and we can step up and step down DC transmission. And it turns out that DC transmission has lower line losses. So in fact, we'd like to be able to transmit our power with DC now. However, presently we have an infrastructure that's based on AC. So that's the electrical transmission story. I didn't tell you about these guys. Yes, Tesla worked for Edison and didn't like him. Edison exploited Tesla, that's what people say. But their important conflict was that Edison said we should keep DC, and Tesla recognized that we would never be able to transmit electricity long distances with DC, so we had to use AC. And he won out in the end. I'm sure the story is more interesting. Please read about it yourself. Thank you.